So I think that today's lecture, even if you've seen quantum mechanics before quite a bit, will be useful because it's kind of an essential bridge between the math that we talked about last week and the qubit manipulation stuff that we're going to be talking about in subsequent weeks. And so I think when you talk about what quantum mechanics is, it is just a mathematical framework, right? It's not on its own, it doesn't tell you anything about the laws of physical systems, but it provides that mathematical and conceptual framework in which to develop those laws. And so for us, our physical system is going to be a qubit. And so the way that we think about quantum mechanics is going to be through that lens. So that's kind of the goal today in large part. So just a couple notes on nomenclature from here on out. So I've mentioned a few times that we are going to be using Braket notation. And I've mentioned before that we're going to represent a vector or state for our quantum system as a ket. So we'll see that quite a bit. Really, the only other thing that's new here that we haven't used very much yet is the inner product notation. So looks like that. In a bracket, two states separated by a line. So I think that's really all that we want to make sure that we keep track of. Okay, so the goal is to get a good working grasp of not all the postulates of quantum mechanics, but only the ones that we really need to understand quantum information. And so we'll start with the first postulate of quantum mechanics, which is all about the state space. It sets up the arena in which quantum mechanics takes place, and that arena is our friend, the Hilbert space. And postulate 1 says that associated to any isolated physical system is a complex vector space with an inner product, that is, our Hilbert space, and we call that the state space of the system. And the system is completely described by the state vector, which is a unit vector in the system's state space. So quantum mechanics doesn't tell us for a given physical system what the state space of that system is, and it doesn't tell us what the state vector of the system is. So we'll kind of put that into context because we're talking about qubits. But and qubits are really the simplest possible quantum mechanical system. And figuring out for a specific system what this state space looks like is a very difficult problem in general, and it is something that's developed by physicists over many, many decades through development of really beautiful and intricate rules and ideas. Think about things like quantum electrodynamics. Like that's a whole field that's conceptualized in the framework of quantum mechanics, but their state space is very distinct from that's used in other physical disciplines. So when we think about these state spaces, another lens to look at this through is to say that every physically realizable state of the system is described by a state function, and that function we usually call psi. And that function contains all the accessible information about the system in that state. And we can define some properties of this state function. We're going to be looking at physically realizable states, so states that we can study in a lab. We're going to be looking for accessible information, the information we can extract from the wave function. And often these functions are functions of position, momentum, and energy, and they're spatially localized. So they're defined things. So the simplest quantum mechanical system, and the system that we're going to be thinking about in this class, is the qubit. And a qubit has a two-dimensional state space. So that showed up on your homework, on homework 1, and so hopefully you guys got to think about that a little bit. And if we suppose that our two states, 0 and 1, form an orthonormal basis for this state space, then we can write down an arbitrary state vector in that state space as psi equals A0 plus B1. And here A and B are complex numbers, and we've seen this equation before. And the condition that our state be a unit vector, when we're talking about qubit systems, satisfies the condition that the inner product is equal to 1. And that's called the normalization condition for these state vectors. So we're going to take the qubit as our fundamental quantum mechanical system. And as you'll see and you'll learn through your My Favorite Qubit projects, our zeros and ones they're real things that we can measure. So for example, in an atom or ion qubit, 0 might be our ground state and 1 might be an excited state, an electronic ground, an excited state. In systems based on either nuclear or electron spin, our ground state might be spin up, and our 0 state might be spin up, and our 1 state might be spin down. And in our photonic qubits, our 0 state might be vertical polarization, and our 1 might be horizontal polarization. So that's, we can write down what those zeros and ones are. But for now, it's kind of sufficient to think of qubits in an abstract form, and for the next few weeks, we'll kind of be thinking about them like that until we think more about the physical systems themselves. So our discussions will always going to be referring to this orthonormal set of basis vectors, the 0 and 1, and we can think about those as being fixed in advance. So intuitively, as we learned in the first lectures of the class, that 0 and 1 are connected to the values, the actual values 0 and 1 that bits can take on. And the way that qubits differ from bits is that they form superpositions of the two states in the form of the state that I wrote down here. So my state psi here is a third physically realizable state of the system. It is my superposition state. And that's what makes qubits distinct from traditional bits. Because of this superposition, like we've heard so far, we can't say that a qubit is definitely in a state 0 or definitely in a state 1 when it's in a superposition. We just have probabilities that it is one way or the other. So we can say that any linear combination of our states is a superposition of the states psi I with amplitude alpha I or AI for that state. And so if we wanted to take an example like this one, 0 minus 1 divided by square root of 2, this is a superposition of the state 0 and 1 with an amplitude of 1 over square root of 2 for the state 0 and an amplitude of minus 1 over square root of 2 for the state 1. So that's really all we need to think about in terms of our quantum information landscape for postulate 1 of quantum mechanics. So the qubit is our state space. Okay, so the second postulate of quantum mechanics asks, how does the state, our initial state psi, of a quantum mechanical system change with time? And the postulate says that the evolution of a closed quantum system is described by unitary transformation. So the state psi of the system at time t1 is related to the state psi prime of the system at time t2 by some unitary operator u, which depends only on the times t1 and t2. So I can write out the expression psi prime equals u times psi to describe my change in the system in time. And this is a discrete expression of quantum mechanical system evolution. I'm just considering two distinct times in time, not continuous. The fact that my operator here is unitary means that my quantum system isn't changing in any fundamental way when I look at its evolution over time. I just have a new picture of the same quantum system. It's been rotated or reflected, but that's it. So we introduce here, I mean, this is the first time we're seeing this term operator, though it came up in discussion last week. So I'll just mention that we want to think about operators as, I mean, they're going to be matrices in our systems. They are used to represent observables, and they're used to obtain physical information about the observable from the state function. So an operator is basically an instruction that tells us to perform one or more mathematical acts on a function. So just as quantum mechanics doesn't tell us the state space or the quantum state of a particular quantum system, it doesn't tell us what our unitary operators are in our particular physical system that we're studying. So quantum mechanics just assures us that the evolution of any closed system can be described in this way. So an obvious question to ask is, what unitary operators should we be considering? And it turns out that in the case of our qubits, basically any unitary operator at all can be realized in physical systems, which is pretty cool. And some examples of unitary operators that act on a single qubit that are important when we're talking about quantum computation are the Pauli matrices, which are represented here. These are quantum gates. So we can see the identity matrix that does nothing. We can see the X, Y, and Z matrices. So the X quantum gate is often called a bit flip gate because it takes 0 to 1 and 1 to 0. A question came up about phase. So if we look at the Z gate here, we are seeing that we're leaving 0 invariant. We'll call this guy the phase flip. We're leaving 0, and we're taking 1 to -1. So we're adding an extra factor of -1, which is going to be called our phase factor. And that's why this gate is often called the phase flip gate. And we'll talk about why next week. Those are just to show them as examples of what this looks like in our case of qubits. Okay, so this postulate requires that the system that we're describing be closed. And we're going to come back to this a couple times throughout this lecture. But that means that it's not interacting in any way with another system. And in reality, all systems, except the universe, which is why I put the universe on the slide, interact at least somewhat with other systems. But we are kind of saying that our system can be described, at least to a good approximation, as being closed. There's all kinds of technicalities about why it's not, but we're going to say that it's well-behaved enough that we can consider it to be. And our systems are going to be well described by unitary evolution, and so we can apply, we can say that we conform the postulate to. You can also kind of get around this by saying that every open system is part of some larger closed system, the universe, that's undergoing unitary evolution, and maybe that's good enough. But yeah, we're not going to get into it more, but I think this is a question that comes up when people are thinking about this postulate, and so it's worth mentioning. Okay, so postulate 2, in the way that I just mapped it out, tells us how the quantum state of a closed system at two different times are related to one another. And that's usually all we care about in quantum information. But you all have probably seen this description of postulate 2 probably more frequently than you've seen the other one. And so this is a more complete, more refined version of the postulate, and it describes the evolution of a quantum system in continuous time. The only thing that I'll mention is that it's worth noting that this description of, this description of postulate 2 uses differential equations, and in quantum information we really don't need them. So they won't show up after this lecture pretty much at all. But it's kind of worth thinking about how this more complete version of postulate 2 connects to our simpler discrete time description. Okay, so here it is. Time evolution of the state of a closed system is described by the Schrodinger equation, which is written here as IH bar times d psi dt equals the Hamiltonian times the state psi. So in this equation, h bar is just Planck's constant. A lot of times it's wrapped up into the Hamiltonian, so we just kind of say h bar is 1, and we simplify it. And if we know the Hamiltonian of a system, then we understand its dynamics completely, which is pretty powerful, at least in principle. And figuring out the Hamiltonian needed to describe a particular physical system can be a really, really, really difficult problem, and is basically the subject of most of the 20th century of physics. And it requires a lot of input from experiments. But from our point of view, that problem is kind of like a detail that can be addressed by physical theories built within the framework of quantum mechanics. And what Hamiltonian we need to describe atoms in such and such a configuration is not really something that needs to be addressed by the theory of quantum mechanics itself. So we don't really care. Most of the time in our discussion of quantum computation and quantum information, we don't need to discuss Hamiltonians, and when we do, we're just going to say that some matrix is a Hamiltonian as a starting point, and we'll just go from there without attempting to justify the use of that matrix as the Hamiltonian. So that's where we're at. Okay, so one interesting feature of the Hamiltonian is that it's a Hermitian operator, and so it's characterized by something called spectral decomposition, which we actually touched on last week, but we didn't use that language. Spectral decomposition is kind of a very useful representation of normal operators, and we say that an operator is normal if the operator times its adjoint is equal to the adjoint times itself. And so this theory of spectral decomposition says that any normal operator on a vector space is diagonal with respect to some orthonormal basis, and conversely, any diagonalizable operator is normal. I don't think that tells you much, so I tried to translate this in other language for myself, at least. And so people often call spectral decomposition eigen decomposition. So what it does is it decomposes a square matrix into the product of 3 matrices. So it takes our square matrix A, and it's going to decompose it into 3 matrices. So it's going to decompose it into P times some diagonal matrix D times the adjoint of P. So P is a square matrix whose ith column is the ith eigenvector of A, and D is a diagonal matrix whose elements are the eigenvalues of A, and that's why it's called eigen decomposition. So because the Hamiltonian has this feature of spectral decomposition, I can write it in this kind of fun, simple way. So I have the Hamiltonian H is equal to the sum over E of E times the outer product of E with itself. So the eigenvalues are E, and they're corresponding to some normalized eigenvectors. And the states, E, those are our energy eigenstates, or sometimes they're called stationary states. And E, the eigenvalue, is just the energy of that state. And the lowest energy is the ground state. And the corresponding energy eigenstate is the ground state. The reason the states are sometimes called stationary states is because their only change in time is to acquire an overall numerical factor. So E goes to exponent minus I et over Planck's constant times itself. So that's all that's happening as a function of time to these states. Okay, so what's the connection between the Hamiltonian picture of dynamics, the postulate 2' that I showed, and the unitary operator picture that I presented first? So the answer can be obtained by writing down the solution to Schrödinger's equation, which we can do in a pretty straightforward way. So we'll say that psi of T2 equals exponent minus I h T2 minus T1 divided by h bar times psi of T1. And so I can re-express this as U T1 T2 times psi T1. And here we just define U T1 T2 equals to that exponential thing on the top. And so then that kind of makes them the same. So the operator that we've defined here is unitary, and it can be realized in this form, U equals exponent I k for some Hermitian operator k. So there's a one-to-one correspondence between the discrete time description of postulate 2 of these dynamics using unitary operators and the continuous time description using Hamiltonians. We mostly will just think about the first one, but because you guys have probably learned quantum mechanics in the framework of Hamiltonians, I think it's cool to draw the connection. Okay, so when we're thinking about quantum computation and quantum information, we are often talking about applying a unitary operator to a particular quantum system. So in the context of a quantum circuit, we might say we're applying the unitary gate X to a single qubit. We're going to do that bit flip that I mentioned. And that feels like it contradicts what we said earlier about unitary operators being or describing the evolution of a closed system. We're applying this unitary operator, so it feels like we're doing work on the system, and that would make the system not closed. And we can think about an example of this, which is shown on the screen. It's when a laser is focused on an atom. After a lot of work in quantum electrodynamics, you could write down the Hamiltonian that describes the total atom laser system. And the interesting thing is that when you write down the Hamiltonian for the atom laser system and consider the effects of that Hamiltonian on just the atom by itself, the behavior of the state vector of the atom turns out to be almost, but not perfectly, described by the atomic Hamiltonian, which has terms related that could be related to things like laser intensity or other parameters of the laser, which we can vary however we want to vary. And so it's like the evolution of the atom were being described by a Hamiltonian that we, as the we applying. So what's interesting about this is that I can kind of understand more about this system, just given different properties of expressions of this type and the fact that my operators are well behaved. So I can say that the completeness equation expresses the fact that the probabilities for my measurement outcomes must sum to 1. And I can actually write down the state of my system after I measure it. Well, I'll write it down here. So the state of my system after I measure it is equal to m little m times psi divided by the square root of psi M dagger, M psi. And these measurement operators that I'm talking about, they satisfy the completeness equation. So M, I guess the sum over M of M dagger M is equal to identity, which is why this is the case. So let's look at an example of how to use this if I'm measuring a qubit in the fundamental computational basis. This is a measurement on a single qubit with two outcomes defined by two measurement operators, M0 and M1. So my operators are the outer product of 0 with itself and the outer product of 1 with itself. Each measurement operator here is Hermitian, and M0 squared is equal to M0, and M1 squared is equal to M1. And the completeness relation we just mentioned implies that M0 plus M1 is identity. So I can write down the probability of obtaining a measurement outcome of 0 for my system. It's equal to this inner product. And that's just equal to the absolute value of A squared. And similarly, the probability of getting 1 is just equal to the absolute value of B squared. And the state that I have after measurement is just equal to A over the absolute value of A times 0, or B times the absolute value, or B divided by the absolute value of B times 1. And these kinds of multipliers, like A divided by the absolute value of A, these things have a modulus of 1, and so they can basically be ignored. That just says that the two post-measurement states are just 0 and 1. I haven't changed them at all. So the status of this postulate 3 as being a fundamental postulate of quantum mechanics intrigues a lot of people because measuring devices are quantum mechanical systems. So quantum systems being measured and the measuring devices together should be part of some larger isolated quantum mechanical system. And so there's a lot of questions, like I said at the beginning, on whether or not you need this postulate to have a complete description of quantum mechanics. Yeah, because the qubit system itself is so simple, extracting probabilities and looking at starting and final states is actually going to be pretty straightforward. Let's talk about distinguishing quantum states. So an important application of postulate 3 is the problem of distinguishing quantum states. In the classical world, distinct states of an object are usually easily distinguished. So if I toss a coin in the air, I know that it is either heads or tails. And that's the only possibility. But quantum mechanically, the situation can obviously be more complicated. And so you can show, and there's a nice proof of this in the textbook, that, for example, non-orthogonal quantum states can't be distinguished. So if we take postulate 3 as kind of our foundation, we can kind of give a better demonstration of this idea. So let's consider a thought experiment that's written up here. So we're going to use Alice and Bob again, and we're going to say that Alice is going to choose some state, psi I, where 1 is less than or equal to I is less than or equal to n, for some fixed set of states known to both Alice and Bob. And she's going to give her state to Bob, whose task it is to identify the index for the state that Alice gave him. All right, so if we suppose that the states are orthonormal, then Bob can do a quantum measurement to distinguish those states. So how can you do that? So he's going to define his measurement operator. Mi is the outer product of psi I with itself. And he's going to write down one of these for each possible index of I. And he's going to write an additional measurement operator, n0, which is defined as the positive square root of the positive operator written there. So those operators satisfy the completeness relation that we just saw. And if the state is prepared, then the probability that I get that state is just equal to this inner product, and it's just equal to 1. So the result that I occurs with certainty, so the result is that I occurs with certainty. So it's possible to reliably distinguish the orthonormal states psi I. So now the question is, what happens if they're not orthogonal or orthonormal? So if the states are not orthonormal, then we can prove that there's no quantum measurement capable of distinguishing those states. The idea is that Bob will do a measurement described by his measurement operators. So let's say MJ with outcome J. And depending on the outcome of the measurement, Bob tries to guess what the index I was using some rule. So like I equals some function of J. The key to why Bob can't distinguish these non-orthogonal states is the observation that the second state, let's call it psi 2, can be decomposed into a non-zero component that's parallel to psi 1 and a component that's orthogonal to psi 1. So if I think that J is a measurement outcome such that f of J is equal to 1, that means Bob guesses that the state was psi 1 when the probability of getting outcome, he guesses that the state was psi 1 when he observes J. But because the component of psi 2 is parallel to psi 1, there's a non-zero probability of getting J when psi 2 is prepared. So sometimes Bob's going to make an error when he writes down his rules to figure this out in identifying which state was prepared. And the book has a really nice, elaborate proof of this idea in box 2.3. So, but this kind of thought experiment walks through the essential idea here. So we are going to always be considering our states as orthogonal if we need them, or when we need them, because we need them to be distinguished. And that's going to be fundamentally true in our qubit systems. So there's two more things that we need to go over. One is the idea of projective measurements, and the other is thinking about composite systems, and that's where we introduce the idea of entanglement. I think I'm going to leave those for next time because I think we have plenty of time.